Hello, this is a video for EDX Statistics 1. It is the third video in this series and we'll look at the goodness of fit test for the Poisson distribution. Here you can see we have some data about the number of text messages that I receive each day for 80 days. And we're asked to see if these results can be modelled by a Poisson distribution at the 5% significance level. Notice that we are only asked to see if a Poisson distribution is appropriate, not a Poisson distribution with a particular lambda value. This means that we will have to estimate lambda from the observed data. It is also worth noting that whilst we are doing this for the Poisson distribution, we can be asked to estimate parameters for other distributions, such as the probability of a success in a binomial distribution. To estimate lambda, we need the mean of the observed data. To do this, we're going to calculate the number of texts times their frequency and add it up, and then divide by the total frequency. This will give us a mean of the observed data of 2.2, so we're going to use lambda equals 2.2 for our model. It's important to remember that as we have calculated lambda from the observed data, this will give rise to an extra constraint when we work out the number of degrees of freedom, so therefore the number of degrees of freedom will be one less than maybe we were expecting. Here are our hypotheses for the goodness of fit test. H0 is that a Poisson distribution is a suitable model for the number of texts, and H1 is that it is not. We're going to need to calculate expected frequencies for each of the possible outcomes of this Poisson distribution. So to begin with, we're going to calculate the probabilities for the Poisson distribution with a lambda value of 2.2. You can do this from your calculator or from tables, but you can see here I've calculated all of these from a statistical package. Now, I've calculated the values from 0 to 12, and obviously 11 and 12 here show that they are 0. Now, these are only 0 to 4 decimal places. They do actually have a value, and in fact so does 13 and beyond. But I don't need to calculate any more of these at the moment because they will all show as 0. And when I'm calculating my expected frequencies, I'm going to be combining categories which have an expected frequency of less than 5. So, now that I have the probabilities for each of those possible outcomes of the Poisson distribution from 0 to 6 and also greater than or equal to 7, I'm going to calculate the expected frequencies by multiplying each of those by 80. Notice that the last category is greater than or equal to 7. It isn't just 7 or 8 like in the original table that we were given, and that's because all possible outcomes for the Poisson distribution must be considered. So that means 7, 8, 9, 10 and so on forever. So our last category in a Poisson goodness of fit test will always be greater than or equal to a particular number. The three circled expected frequencies you can see are less than 5, but if I add those together I will get a single category of greater than or equal to 5, where the expected frequency is greater than 5. The next thing I need to consider is the degrees of freedom. So I will have the cells from 0 to greater than or equal to 5, which is 6 cells, minus the constraint for the total frequency, so that's -1, and minus another one because we had to calculate the mean from the observed data. So that's going to give me a total number of degrees of freedom of 4. The next thing I find the critical value for the hypothesis test. We were asked to carry this test out at the 5% level and we have 4 degrees of freedom. So as you can see, our critical value will be 9.488, so we will reject H0 if our test statistic is greater than this value. The next thing I'm going to do is calculate the test statistic. So for each of the k values I'm going to calculate O minus E squared over E, which I've done here, and then add those up to give me a test statistic of 2.1016. I'm now going to compare that to the critical value, And as you can see, 2.1016 is less than our critical value of 9.488. So there is not enough evidence to reject H0, which means that the text may be modelled by a Poisson distribution with a mean of 2.2. That's the end of this video. The next video in this series is on contingency tables.